So I'm Paul Wright, and I'm currently working with SpaceML as a curator and researcher. Prior to this, as a postdoctoral research fellow at Stanford University, where I worked alongside the Solar Dynamics Observatory team. For the past few years, I've also been involved with the Frontier Development Lab as both a researcher and mentor. In this talk, I'm going to introduce the Solar Dynamics Observatory, the Solar Dynamics Observatory Machine Learning Dataset, SDOML, and specifically SDOML on SpaceML. I would kindly ask that questions are left until the end, where we'll have about 5 minutes to answer any questions. So I'll start by providing a summary of the talk, followed by an overview of the Solar Dynamics Observatory and where the SDOML dataset fits in. Following from the SDOML introduction, we'll discuss SpaceML, the SDOML notebook hosted on SpaceML, and finally highlight a project that uses the SDOML dataset. Before we dive in, I want to take some time to quickly summarize the main points of this talk. So SDO has 3 instruments. Each instrument observes the sun at varying wavelengths and varying cadences. Since 2010, SDO has obtained over 500 million images. This has resulted in a petabyte-scale dataset ideal for computer vision and machine learning applications. While this data is easily accessible, pre-processing this data requires specialized scientific knowledge. To address this, we present SDOML, and specifically here, SDOML on SpaceML. SDOML is a cleaned, curated dataset covering the entirety of the SDO mission from 2010 to present day. SpaceML brings together data storage through Google Cloud, compute through Google Colab and the Google Cloud Platform, and well-commented version-controlled notebooks for data access and reproducibility. So the Solar Dynamics Observatory consists of 3 instruments, as I've mentioned, and the first of these is the Helioseismic and Magnetic Imager. SDO observes from the visible solar surface up to the diffuse hot atmosphere known as the solar corona. We will start at the photosphere, the visible solar surface, with data obtained by HMI. In this video, and the ones that follow, they will last for 20 seconds and correspond to 2 days of observations. To demonstrate scale, we also show the size of the Earth in the bottom left corner. As the sun rotates, sunspots, the dark blemishes, appear to cross an otherwise featureless surface. However, at smaller scales, we can see granulation due to convection cells. This starts to highlight an important point of this data. The sun has features across a wide range of scales, both in terms of their lifetime and their physical size. Sunspot groups can persist for many weeks, while convection cells last for tens of minutes. In addition to observing the photosphere, HMI also produces maps of the sun's magnetic field. Shown to the right is the line of sight component derived from the full vector field. In comparison to the previous data, the dynamic behavior is more clearly visible here. We see magnetic field emerging and disappearing. In these data, white represents outward magnetic field, and black represents negative inward magnetic field. These large black-white regions correspond to regions of sunspots in the previous video, and the pairing of these regions is due to magnetic field penetrating the surface and looping back down. Outside the strongest regions, the apparently gray background could almost be forgotten about, but again, at smaller scales, there is almost a salt and pepper-like pattern of positive and negative field. The second of 3 instruments on SDO is the Atmospheric Imaging Assembly. SDO AIA observes the solar corona, the diffuse solar atmosphere, and it is in these images where the true dynamic behavior of the sun can be seen. AIA has 10 channels, ranging from 5,000 to 6 million degrees Kelvin. Here, we show the 171 angstrom channel, centered at approximately 0.6 million Kelvin. The corona is filled with high-temperature loops connecting the regions of opposite polarity we showed before. When these coronal loops move, they can result in explosive release of energy that bombards the Earth with ionizing radiation. However, predicting the occurrence of these events, known as solar flares, is an unsolved problem in heliophysics. While the high-temperature plasma is seen all along the magnetic field loops, this high-temperature plasma is seen all across the sun too. How the sun is heated to and sustained at these temperatures is a problem known as the coronal heating problem, one of the great challenges in astrophysics. To emphasize AIA observations more, this image shows the atmosphere at 1.5 million degrees Kelvin, double the temperature of the previous data. In these data, it is now clear that there are regions of the sun that are much cooler than the rest of the sun, such as the region at the top known as a coronal hole. And the reduced contrast between the active regions and the background highlights that the majority of the atmosphere sits at around 1 million degrees. From the 4 videos of these 2 instruments, there are clearly some artifacts you may have noticed. The full sun occasionally dims in these images, and this is due to the exposure time being a variable. The image jitters around slightly due to the telescope correcting in space. Eclipses of planetary bodies occur, as you see in this video, and instruments are sometimes offline. The third and final instrument on SDO is the Extreme Variability Experiment. SDO EVE provides sun-as-a-star observations in the extreme ultraviolet. As shown to the right, EVE observes the solar spectral radiance from 5 to 110 nanometers. Unfortunately, the MEGZ component, which contributed measurements near the SDO AIA overlap, that's shown in red in the figure inset, ceased operation in 2014. As SDO AIA produces images over similar wavelength ranges, machine learning has been used to nowcast EVE irradiance from AIA. So over the last decade, SDO has enabled countless advancements in our understanding of our closest star. There's incredible potential for both statistical and machine learning approaches, and we hope to answer some of the questions such as the coronal heating problem. While it is generally advisable that data corrections are left to the user, in this case, the pre-processing may act as an unnecessary hurdle for those wishing to experiment. To address the issues that we mentioned in the previous slides, we present the SDOML Dataset. The SDOML Dataset includes data processing such as rotation of images to solar north, co-alignment of images taken at the same time, correction of the Earth's elliptical orbit, and correction due to AIA degradation. This last point is important, as we know that the degradation of EUV filters in space occurs over time. This reduces the apparent brightness of the sun. The resulting cadence is we take AIA from 12 seconds to 6 minutes, we leave HMI at 12 minutes, and have EVE data at 1 minute cadence. The 2009 paper provides version 1 of the SDOML dataset. It ranged from 2010 to 2018 and was stored at a size of 7 terabytes on the Stanford Digital Repository. In this case, we only stored the image arrays without metadata. There are a number of problems with version 1, however. The data is, 1, stored away from the appropriate computing resources, and that means that downloading is required. The 7 terabyte size can be prohibitive, there are no demonstration notebooks available, and there's no metadata associated with the images. We therefore present version 2, SDOML on SpaceML. This ranges from 2010 to present day, and the data is stored in the ZAR format, where ZAR is a chunked compressed n-dimensional array. This includes image data plus metadata and is stored on the Google Cloud platform. The small dataset is freely accessible through SpaceML, and the complete data access is available on request. In addition, we've updated the degradation curves based on the latest correction tables, and there are provisions in place to continually update and version this data. So SDOML combined with SpaceML enables an easy entry point for those wishing to apply machine learning techniques to this data. The user can use just the image arrays, as with version 1, or even incorporate the metadata information. So before I demonstrate data access, I want to introduce SpaceML and how you'd navigate to the notebooks. So SpaceML is a machine learning toolbox at developer community building open science AI applications for space science and exploration. SpaceML hosts a number of freely accessible datasets for scientific analysis, including SDOML, and there are project pages that demonstrate published results with reproducible notebooks. To learn more about SpaceML, visit spaceml.org. So if we go to SpaceML website, you'll be greeted with a number of projects. Clicking through to the SDOML project leads you to an overview and a button to open the notebook in Colab and in GitHub. In the following slides, I'll walk through a pared-down version of the SDOML Colab notebook. We'll introduce how to access data and plot both the image arrays and SunPy maps. As we've already gone over the introductory material, we will start halfway down this notebook. First, we need to install ZAR, as this is how the data is stored, SunPy, to demonstrate creating a SunPy map object, and GCSFS, to interact with the Google Cloud Storage. In this notebook, we also utilize Dask, an open source library for parallel computing. In cell 3, we provide the location of the subset of the SDOML dataset from August 2010. This example will concentrate on AIA, but the process is very similar for other instruments. To access this data, we first instantiate a ZAR group in cell 4 and can visualize how the data is stored in cell 5. From the hierarchy, we see that it's stored per year, per wavelength channel. We see that the SDOML data for August 2010 consists of about 6,512 by 512 images stored as float 32. So as we know the structure from the hierarchy, we can easily access and load as a Dask array. From here, the data can be manipulated as with NumPy. As a slight aside, cell 7 lets us visualize how this data is stored. The total array for August 2010 for the 171 action channel is about 6 gigabytes in total. It is therefore stored as 52 chunks of 125 megabytes. So for those of us that just want to use the data as is, we can just index the Dask array as with NumPy and plot as usual. In this example, we select the 6,000th image, obtain the appropriate color map from SunPy, square root the data due to the large dynamic range, and then plot with matplotlib. As version 2 of SDOML contains header information, we can also select to subset the data using one of the keywords. For here, we'll use exposure time. So in cell 9, we create a NumPy array with the exposure times and plot this as a function of index. We see that this exposure time does vary slightly over the year. With this in place, we may want to select all the images with an exposure time less than 2 seconds. We do this as follows in cell 11, and we can then plot we can demonstrate the data as in cell 12, where the selected images array now contains about 4,000 entries versus the original 6,000. The last thing that I want to discuss is that for those who want to integrate SDOML into your normal workflow, you may want to manipulate the data with SunPy. SunPy is the open source library for solar physics analysis. As version 2 of SDOML contains header information, we can extract the data and the fits information as a dictionary, shown in cell 13, create the SunPy map, as shown in cell 14, and finally in cell 15, we can plot the image. Compared to the image before, we note that the axes are now in physical units and the observation data is included. And this is where I'd like to leave the demonstration for today. If you'd like to see more examples, I would recommend visiting spaceml.org. In the full notebook, we show examples of making animations, loading, and manipulating the HMI and EVE data. Before I conclude this talk, the final component of SpaceML that I wanted to mention is the number of projects that utilize this data. If we navigate back to the SpaceML webpage, we can see a number of project cards. Two of the SDOML related projects are temperature maps of the solar atmosphere, where we recover the temperature distribution using SDO images, and the SDO AIA autocalibration. Here we use a convolutional neural network to self-calibrate AIA. In the next slide, we'll take a look at the SDO autocalibration result. So we know that EUV images instruments degrade in space, and as a result, sounding rocket flights are occasionally flown to calibrate AIA. While these flights are extremely helpful, the data is interpolated between successive flights. In this work, Dos Santos et al. Use a convolutional neural network that takes either a single AIA channel or multiple AIA channels and outputs a corresponding degradation factor or multiple factors for the multi-channel version. The notebook goes through reading and loading the SDO AIA data before performing inference with the multi-channel model. With inference performed, we create a degradation table and apply this to the AIA data. The figure at the bottom shows a 304 angstrom channel, the channel that suffers the most degradation over time, plotted on the same color scale, left to right, once a year from 2010 to 2020. The top panel shows as observed with the degradation leading to the apparent dimming of the sun over time. The bottom panel shows the ML corrected data using the ML autocalibration method. This is a really nice result, and it shows how machine learning can be used to self-calibrate instrumentation in space. So to summarize this talk, SDOML is a cleaned and curated dataset covering 2010 to present. Version 2 of SDOML is available on SpaceML, and the notebook in place to demonstrate data access. You can easily access the small subset, and the full dataset is available on request. SpaceML provides ML projects that use SDOML along with notebooks to reproduce the results. On the right, I provide a number of references to the works that I've discussed here, from SDOML original paper, from Galvez et al., to nowcasting SDO EVE with SDO AIA, to the SDO autocalibration that we've just touched on. So before I open up for questions, SpaceML is a machine learning toolbox and developer community where we build open science AI applications for space science exploration. You can find out more at spaceml.org, and this work was made possible by NASA, SETI, the Frontier Development Lab, and the many collaborators that helped with the work that I've discussed herein. Thank you for your time, and I'm happy to answer any questions.
Yeah, thank you for the talk, Paul. That was very nice. I'm wondering whether the processing steps that you do at the SDOML dataset, whether they're standard in heliophysics, and whether like having this preprocessing will help make different works in heliophysics more comparable.
Yes, so these are, I would say that they're standardized processes. There are other processes that you can do that are probably not relevant here. But one of the problems we've seen with some work is that they've scraped, say, JPEGs from HelioViewer. So the videos that I showed, they would scrape the images from HelioViewer, and then they're no longer scientific data. What we're trying to do here is process the scientific data to a point where anyone can use it without too much knowledge. And then basically with that data, we like each pixel is then a physical unit, if that answers your question.
Yeah, thank you.
Yes. You mentioned that the data is ready for download and request. So do you have an estimate how long would it take to download the full data set?
So the full data set, I'm assuming Mung may have a better answer, is probably about at this point like 10 terabytes. The point of having it on the Google Cloud Platform would be to use it in place rather than to download it. So the way I would probably interact with this data is through either a notebook of the Google Cloud, the Google Colab, or spin up a virtual machine on the Google Cloud Platform. So I don't know how long it would take to download, but the idea of having it on SpaceML and in the Google Cloud ecosystem is to use it in place.
Yeah, thanks. Nice one, Paul. Do you as part of the prep work for having the data to be ML ready, so to speak, involves writing some code for serving the data in a data set, data loading it into a model and stuff like that.
Yeah.
A lot of technical little things. Does this data also come packaged with some code for training, say, PyTorch models?
It currently does not, but that could be something that we incorporate, and I think that's a really good idea. We have the code in place and on GitHub to process this data, but that would be a good thing to add. So currently there are some notebooks that load in the data, but it'd be good to have like a data loader that someone can just use. I think that'd be great.
Hi, yeah, this is Meng. And thanks, Paul, for the very nice talk and the great efforts you did for SDOML dataset. And I think SpaceML is doing an important work to contact the space science and data science community. So my question is, if someone has developed a ML model based on the dataset on SpaceML website, like SDOML, what is the typical procedure for request deploying the model on SpaceML? And is there an application process? And what kind of resources SpaceML would be able to provide, like some GPU credit for deploying the model?
I do not really know the answer to the latter part of that question. Maybe Anshul will be able to answer if there's any available credit to run things on SpaceML, but I'm happy to discuss with anyone who wants to put a notebook up onto SpaceML. And yeah, I don't know if Anshul, you have any input there.
In terms of credit, at the moment, we are looking at this on a request basis. So it would be that you put forward a request for why you want to use the data and what you're trying to achieve with it, and then it would get approved. This isn't something that is just open to everybody. As you can understand, credits go really quickly. But if there is legitimate interest and a relevant project, then we'd be happy to take any applications and consider how we can help in terms of credit or facilitate that for you.
Thank you.
Okay, I think that was it. Thank you, Paul, and for an amazing first talk. This was really great. And also thank you everybody for coming to attend and joining us on our inaugural SpaceML speaker series. We're hoping to make this a monthly event with different speakers, different topics, and really bring valuable content to not just academics like yourselves, but also to the greater SpaceML community. The more knowledge we can share, the better this community will be. So I really appreciate all of you taking the time to join us and taking the time to enjoy this presentation. And thank you, Paul, for putting it together.
Thank you so much.
Just another note, if you do think of questions that you would like answered later on, in January, we'll be sending out an invite closer to the time. But in January, Paul will be holding office hours on the SpaceML Slack channel. So if you've got something, a burning question, there'll be time for you to be able to address that. And also, I believe Paul has a plan to go through a live Colab notebook at that time and just walk someone through a live example. So you will have that opportunity as well.